today we're going to talk about rate laws for multi-step mechanisms. So the reason for that is because most reactions that occur, they actually occur with greater than one elementary step. And if you can recall what the definition of elementary step means, it means that the reaction is occurring in that one step. So if we are to write the rate law expression, we can do it in terms of that one elementary step. But that doesn't always happen in real life. In real life, we have more than one step in a true chemical reaction. So we have to be able to figure out how we can write a rate law that uses that. So the first thing that is really important is the rate determining step, which is commonly abbreviated as RDS. It's also called rate limiting step in some textbooks, but it really means the same thing, which is the slowest step of all the elementary steps that take place in the reaction. So this, of course, governs the overall rate law for the overall reaction. So if you think of any analogies such as being stuck in traffic, the rate of your overall trip is how much time you spend in the car, not if it only takes you about 10 minutes to get from point A to point B. So this is the reason why we use the rate limiting step as the step that's involved in the overall rate law expression. So let's consider, for example, the reaction of nitrogen dioxide with carbon monoxide. Our experimentally derived rate law was found to be second order in the concentration of nitrogen dioxide. But however, we're going to propose that this happened with the following mechanism, where in step 1, we have NO2 and NO2, which we put a little K1 on top, which means that this is the rate constant of the first step. The subscript 1 means that it's the first step. This is noted in the question as being the slow step. The second step, NO3 plus carbon monoxide, K2, because it is step 2, that's where the subscript 2 comes from, gives us nitrogen dioxide and carbon dioxide. This is the fast step. Note that NO3 is an intermediate. So this guy right here is an intermediate. So an intermediate, you remember, is something that is formed in one step and then is consumed in the following step. So another thing to note is that if K2, so your rate constant for step 2, is a lot larger than the rate constant for step 1, this means that the rate of step 2 is a lot faster than the rate of step 1. So please note that when we're talking about rate constants, we're really talking about the overall rates. So the overall reaction rate will depend on the first step, which is the slow step. So our rate expression, because it has to be consistent with the slow step, is consistent with the experimentally shown rate law. However, just because it is an agreement, that doesn't mean that we actually proved the mechanism. So when we move over to the next board, we're actually going to prove this mechanism, that it is true. Okay, so let's consider another reaction. This one, for example, will be 2 nitrogen monoxides plus bromine gives us 2 NOBr. Our experimentally derived rate law for the reaction is second order with respect to nitrogen monoxide and first order with respect to bromine, which gives us an overall order of 3. Let's look at the steps. The first step, NO plus Br2, gives us a double-sided arrow, which means that this is in equilibrium. And I put a K1 on the top to show that it is step 1, and a K to the negative 1 underneath to show that this is step negative 1. This is the fast step. The double-headed arrow means that this is in equilibrium. We'll talk about that in a brief second, what that means. Step 2 is the slow step, and we have NOBr2 plus NO. Second rate constant gives us 2 NOBr, the slow step. So if we are to write a theoretical rate law, our theoretical rate law has to be in terms of the slow step. So the way we show that is that rate is equal to K2, the rate constant of the second step, times the concentration of the reactants. But notice that there's a problem here, because one of our reactants in the slow step is actually an intermediate. And our intermediate, we cannot weigh out. We don't know how much of it actually forms in the reaction. There's an unknown concentration, which means that we are not able to easily manipulate it. So in order for us to be able to get rid of the intermediate from the rate expression, we have to exploit the first relationship. So our solution is, we're going to have a look at what equilibrium actually means. So we know that step 1, the rate of the forward reaction equals the rate of the reverse. This is by nature the definition of that double-headed arrow. It means that as soon as the product forms, it reverts back into the reverse reaction. So we know that we can figure out how to rewrite this expression in terms of the true starting materials, the true reactants of the reaction, allowing us to get rid of NOBr2. And the way we do that is we show rate of the forward reaction equals the rate of the reverse, which we showed K1 times NOBr2 is equal to K to the negative 1 times NOBr2. Notice that these are both the reactants with both of the equilibrium expressions. We can now isolate for NOBr2 using this relationship, which we end up getting K1 times NO times Br2 divided by K to the negative 1. And now we can use this relationship. Notice that this is written in terms of the true starting materials, of true reactants in step 1. We can now substitute this into our theoretically derived rate expression. So I'm going to move the board over. Which is exactly what we did here. Notice that we substituted NOBr2 into our expression. So we end up getting K2 times K1 divided by K to the negative 1. Substituting all the values in gives us a rate law expression that is consistent with what was given to us in the question. The K2 times K1 divided by K to the negative 1 is really arbitrary because it just means K. You can just write overall K. And now we have proved that this expression is actually true. It's not only consistent, we've done a mathematical proof. So that's a way to answer this question. And that's it for today.